we can get started. Well done, everyone who came in person this morning with slightly less nice weather than was yesterday. And I expect we might have a few more people on Zoom today, but we're going to get started. So we have session 4, this session this morning, 4 talks, and then morning tea. Maybe not exactly where we had it yesterday. I'm not sure if they will, if there'll be too much rain, but somewhere just out there. And then another session before lunch and posters in the same place as yesterday. So I'll hand over to Professor Dre Lee, and he's going to give the first talk. Do you want the chat there? Chat will be on the screen if you want.
Oh, yeah, there is something.
You can just look at it later.
Yeah, okay.
Just put this down.
Yep.
Okay.
Okay, good morning, everyone. And I thank you for the invitation for this talk. And this is my topic today. Firstly, acknowledge traditional land owner and their custodianship of the lands on which we meet. So my topic is about how to apply AI in evidence-based medicine. And in this case, we consider why should we using AI? We never, about 10 years ago, whenever I started talking about using machine learning AI to the doctors, they are really reflected very negative. And once I talked to a professor in Melbourne University, and I said, can we do AI within the hospital ICU? He said, don't do it, because you don't have the data. Government doesn't allow you to do. Doctors is not going to collaborate with you. And fourthly, it's very difficult. Don't do it. And I feel a little bit happier, because if nobody doing that, I still got a chance, because all of those 4 reasons never said this is not worthy, this is wrong, or this doesn't have a value to our society. It's just the difficulties. So why not I overcome those difficulties, and then I have a chance. And that is why I started to talk to the doctors in Royal Brisbane Hospital. And one of our collaborators here, Robert, both. And together we applied ARC discovery, and I got a postdoc, and I also got a PhD, and they are all graduated now, working on the ICU using AI. So today I'm going to discuss our understanding of that, and also the work done by our team. And also this project is sponsored by UQ-AI Collaboratory, and we have a prototype system already implied and implemented and still going on, and to make it much close to reality. So this is what is evidence-based medicine. And firstly, what is evidence? If you tell me a fact, those facts are evidences? Probably not. For example, if you say, okay, there is an ICU in a hospital and they got 0 death in a year. And that fact, if using that fact as evidence to justify this is a good hospital or good ICU, is terribly wrong, because if you look at the further details, and this hospital reject the patient into the ICU if they feel this patient will die in their hospital. It is fact, they got a 0 mortality in their ICU, but that fact is not the evidence to justify this is a good hospital. So we would say evidence is verified, tested, and justified evidence or facts for the medical decision making. And that is here is a definition. Evidence-based medicine was there for many years, since 1991. And many people are discussing evidence-based medicine against immunance-based medicine. So-called immunance-based medicine, that means it is experience-based. It is heuristic-based. It is based on some prominent, very experienced, older or whatever doctors who have a lot of experiences. And evidence-based medicine means we need to use external evidence, maybe just recently available, but that doctor probably didn't read too much because the literature of global pandemic publications are coming all the time. How can you sure you can adopt the most advanced or verified techniques for the patient? So this kind of a different attitude towards the medicine is changing because more and more people believe. What's wrong? Sorry. Evidence-based medicine probably more objective and also for the effectiveness and the efficiency of that of the patients. But also people talking about precision-based medicine or precision medicine. And the precision medicine means the personalized treatment and also the patient's DNA information. A lot of individual information will be applied during the decision-making process. Here are some examples. For example, coronary artery bypass grafting operations here. Different patients may have a different outcome. And also on the right-hand side, if there are so many patients for the same operation, average is the middle of the line. So which patient would get the most survival rate after 20 years, for example? So evidence-based medicine is approach which we appreciate external evidence. However, we still need to make that personalized. So there is no contradiction. It's just the evidence-based medicine would be applicable to precision medicine. So this is the situation we are dealing with. Now we are thinking, if evidence-based medicine can be computational, can have a decision-making model, and then we apply the machine learning AI technology to help the decision-making process during those life-critical situations. And then we look at what is a roadmap of AI. Firstly, we do the data fusion, data linkage, and also consider quality of the data, alignment of the time series data, and also consider data privacy. After that, we do the learning. And in cognitive science, machine learning means you understand those labeled or unlabeled, structured or unstructured data in multimodality and learn the patterns out of those raw data, such as decision trees, knowledge graph, and Bayesian network or probability graph models, and the time series patterns, and so forth. And they are the obtaining of the knowledge. After that, we need to apply knowledge to the decision making. We call the reasoning and take actions. Ancient philosopher Aristotle said, probably it's overly simplified, the human thinking patterns has 4 different styles: deduction, induction, abduction, and inductions. Deduction means you have a fact or evidence, you have a rule, and then the new fact can be derived. Induction means you have the facts. You wonder what is a rule you can generalize from that pattern or from those facts. Abduction means you know the consequence, but you wonder if there is a reason for that consequence. And that is not irreversible. Sometimes you got like a car, you cannot, the car doesn't start, but does it have a petrol or does it have electricity? There are different reasons. So abduction needed to be further verified. And induction is a case-based reasoning. You have cases like A implies different consequences. You wonder those different consequences got a similarity between them. Or the different conditions implies the same consequence. Then you wonder those different conditions would be similar or have some kind of correlations. So it is basically so-called reasoning is a connectivity of those different types of relationships, such as association, correlation, covariance, contravariance, causality, and the dependencies, and so forth. They are all mathematically different. And finally, we also consider data visualization for AI. So we use AI in life-critical situations. And then there are some concepts related to this. First one is called AI with the human in the loop. There are our professors doing this kind of research, like Januka. This research focus is here. AI with the human in the loop means the decision process would involve the human individuals or experts. And the human is a component, a part of the decision process. Human-centered AI means the AI is not going to replace the human expert. It's to provide services. The purpose is to serve the human. And those two concepts are slightly different. And then we have this kind of situation. According to the path of cognitive science, we have a perception, cognition, learning, reasoning, and take actions. And this is the life cycle or some different scenarios within our human-involved decision-making process. And machine learning and AI would participate within that. And also we use discovered knowledge as a logic graph for that situation. So what are the challenges in order to do the evidence-based medicine by using AI? There is we call the equilateral triangle, LPS triangle. You have a big data in the middle. They have a distributed ownership. Different organizations own their own data. And then in order to learn the patterns, know the global pictures, you need to share multiple data sources. And also you need to respect the privacy. If you look at this triangle, any two of them probably is okay. You can combine in two parts and find out solutions for that. But so far, we haven't seen any algorithm can deal with both all of those three things together. And that is the challenge we are facing. For example, if you share the data with the privately owned data, then you need to do the data linkage. And after data linkage, then you do the machine learning. And after machine learning, how do you preserve the privacy? And there are so many difficulties. And in order to present our solution, probably I needed to discuss a little bit about why do we need evidence-based medicine anyway. People made mistakes, first positive and first negative errors. If you have a stroke in the home, you call the ambulance, come to your home, and the ambulance, what's called paramedicals need to make a quick decision whether it is a bleeding or it's a blocking. If it is a bleeding, stop the bleeding by giving some medicine, or if it is a blocking, then you dilute that block. If you got it wrong, the people die immediately. But how do we know which way? It's a blocking or bleeding. The golden rule is using CT scanning. And CT machine is big in the hospitals. Then that means you need to spend 10 minutes to go to the hospital. And that 10 minutes probably is very, very critical. And then which way you believe? Stop the bleeding or stop dilute the blocking. So that is a situation very life critical. False positive or false negatives needed to be considered as a trade-off. Sometimes you trade your false positive for the false negative errors because it is life critical in some situations. And also there is a lag between the research publications and the clinical applications. As we know, the global pandemic has a lot of publications. And how do the doctors treating COVID-19 disease in a timely fashion using those mostly available or recently available things? And people say average time for medical research to be accepted into clinical practice is said to be 17 years. And that is too long. So we need to use external evidence. But when you tell the doctor there is external evidence, doctors probably say, I knew that 10 years ago, why you tell me this kind of thing? So doctor doesn't like to be told those things they already knew. So what we can do? This is a third party service. So AI would be sitting there like a cup of tea. You want to drink? It's there. If you don't, that's fine. I'm there, whether you want me or you don't want me. And then the responsibility of that decision would be the doctors. And also evidence-based medicine is not a cooking book, but an improvement of our traditional medicine. So this is a practice of evidence-based medicine in general. Formulate your answerable questions, finding the evidence to formulate the answers, and also access that. And finally, you need to do the evaluation. So this is a standard procedure in evidence-based medicine. However, we need to use AI to support that process. And if you look at those step-by-step procedures in the evidence-based medicine, they are mostly computational, search, computing, and make decisions. And why not we use AI? So we consider this is our proposed solution to solve those three pairs of the problems together. For example, learning on the private or different owned data sets, we use federated learning. And I don't want to discuss on the details of this algorithm, what is a federated learning. And in deep learning, the different sources are owned by different owners. And then the deep learning model will be uploaded on the client side, on the owner's side. And then you learn after that, the gradients will be uploaded, those parameters you learned will be uploaded to a global learner in the server side. And also learning on shared data, because in the supply chain, for example, a lot of different types of the data are shared by different owners. And if you learn to the shared data, then you probably need to consider multimodality learning. And that means you can learn on the integration or fusion of audio, video data, image data, text data, and time series data as well. And also, with respect to the privacy, you still want to share your data. What is the solution? And there is an algorithm, very famous algorithm called the differential privacy. And currently, differential privacy was regarded as the #1 or best government approved algorithms. And almost every mobile phone now is using this algorithm by Apple, by Facebook, by every service providers. They are using differential privacy. And so this is our solution. We're trying to create a learning model. And that learning model consider data privacy preservation, consider sharing of the data, and also consider the learning of the global prediction model. We call the machine learning model. This can be generalized to a solution for sharing big data over all different organizations, like a defense department or national security department. They want to share taxation office data, they want to share health data, they want to combining your driver's license with your passport number. And then how can we do that? And the solution is already there, differential privacy. And then how can we guarantee the privacy preservation and still sharing the data? And then how can we combine passport number with a driver's license number? We're using quasi-identifiers. That means your home address, your name, and your date of birth will be used to link those different sets of data and still guarantee the privacy. And this is already accepted by European GDPC and also accepted by American government census data, the government Bureau of Statistics. And this is our proposal. I don't have time to detail that, but this is our ARC discovery project waiting for the outcome probably next week. We will know whether we get accepted or not. If not accepted, then we are going to apply it again. It's not easy, 20% of acceptance rate. Okay, so what is a differential privacy? We apply differential privacy for sharing data link the quasi-identifiable data. And as you can see, a lot of organizations are already using these algorithms like 2020 US government census data, European GDPC data, Android, and also different companies. Every big company is using that. If you read the fine print of those privacy preservation policies, they always say in the bottom, they said that we use differential privacy algorithm to protect your data. What's that mean? Here, the principle in differential privacy is the deniability by randomization. That means if you want to know, do you smoke? You don't like to tell me whether you are smoke or not, but that's fine. I introduce the noise by giving you a coin, you toast. If it is a head, then you tell me the truth. Otherwise, I introduce 75% of the noise of that. And after I collected your true data and also the noise data together, and I can still do the accurate statistics based on this data collection process. And that is an idea from the differential privacy algorithm. And this is a computational formula. And also that means the data set D without your data, D prime with your data would generate the same data analytical result. And that implies you can happily deny, say, my data is not there. That is not compromising my privacy. And by introduce the noises, of course, then you need to control the threshold of that noises. And then there are so many different opportunities in evidence-based medicine. For example, we are talking about all of those treatment, personalized privacy preservation, and so forth. And the common sense used in the decision making. And also, if you do the privacy preservation data linkage, still preserve the privacy. And there are so many data sets are available for you. And some of them are openly available. Some of them you need to apply after the ethical approval process, approval of ethical clearance. And then also we use medical records for the finish. Yeah, okay, sorry. Okay, so we need to introduce an inference engine to do this, and that is something we call the high order reasoning. High order reasoning means it is different from low order. High order reasoning to consider what if, why not, and so about, and this is the idea of our prototype. This prototype means I can challenge your conditions, challenge your method you are using, and challenge the outcome or significance, and also different applicability. And this is our component, our contribution. We call it AI as a service. And this is our actual system. And if you go to this website, and then you can see our actual system. And there are different applications and so forth. And this is developed by many of my students and the postdocs. And all of those things are currently available. And currently we are also create a chatbot and as a representation of the high order reasoning, and talk to the doctors if you make decisions, and make sure your decisions can be challenged by high order reasoning. And this is the ideas. We automatically summarize the report for nurses. If you edit it and submit it, and then we will learn from that by reinforce the learning. Okay, so that is the system demo we have. And this is the publications we have so far, and also the contact details.
Thank you. Okay, so we might. Yeah. And we have the next speaker.
Thank you so much. It's a nice presentation. I have one question. So you wanted to apply the
Yeah, I think so. Yeah.
you wanted to apply the credit different. So do you consider how do you transfer the data from the client into the cloud? How do you transfer the data, like process data, which is the client would like to transfer from client to the server? The client to server.
On server? Oh, okay. Now data, there's no data to store in is learn the line. That is only our weights of the layers. Just weight of your neural network. Yeah, this is controversial, but very capable.
Do you use any specific technology to transfer the data, like the process data from the client to the server, and using the IoT system, your system, or using the some outside?
Yeah, so we had student graduated for suicide prevention. How can you get the suicide rate more for conditions of the server? It's very time sensitive, but we still want to take it to this suicide.
Okay. Thanks again, Chuck. Yeah, that's what we're.
Present it again, then I can struggle.
Good morning. Can you hear me?
Yes.
Oh, okay. Good morning, everyone. My name is Thuy, and I'm a first-year PhD student under the supervision of Dr. Stephen Bowman. And today, I want to present to you our project, which is to develop a browser-based deployment framework for medical imaging AI models. So in medical area, but due to the time-consuming diagnosis process that might be prone to subjective interpretation, medical experts started to benefit a lot from computer-assisted intervention. So that's where deep learning began to emerge in medical area. So it's here to help medical experts to do a lot of diagnosis tasks like detection, segmentation, prediction, and image reconstruction. Deep learning is helping to increase the quality and also reduce the cost in healthcare system. And the model input from deep learning model in medical area is including but not limited to MRI, CT, and X-ray. So it's a bit slightly different from natural images. And that's why it's best to bring deep learning model closer to clinic setting where the user have all the tools in their hands, and that would fill the gap between user and deep learning models. And it's also optimize the model performance with the user feedback. So you're gonna have feedback from doctor and clinician directly because they're gonna have the output from their side. And by that, we also promote the openness in science. But why is it hard to deploy deep learning model for medical imaging data? The first obstacle is regarding patient data. So it's very complicated to share new data or have a centralized database in the server because it has to comply with HIPAA in the US and GDPR in Europe. So it's very hard for researcher to test model on new data. And another difficulty is that researcher who develop the model may not have as much experience as medical experts to do the diagnosis. So they have to depend on a lot of different metrics, and the metrics might not be comprehensive enough to validate the models and give the best accuracy for it. Another thing, as we discussed yesterday, is that in the current landscape of state-of-the-art architecture and deep learning, even researchers may find it difficult to keep up with. So it's very difficult for medical experts to tweak the model, optimize it, and deploy it themselves. Sorry for that. And they even have a large amount of medical image on their side and the ability to validate the model performance. Unfortunately, they cannot do anything about the model. So it's best to get their feedback, and then the researcher would optimize the model. Another challenge is to have an easy to use interface for clinician to test the output directly on their side. Medical imaging could be a bit more complicated because we have to handle a lot of different aspects within an image itself. For example, how to find a file transformation and the intensity contrast within an image. So it's ideal to have an visualization tool for clinician to see it after the inference, because they're not familiar with developing tools like TensorFlow or PyTorch to run inference and then visualize it with Matplotlib like a researcher can do. Finally, there's a gap between hardware resources in different settings. So it would be ideal to have an inference runtime that supports CPU, which is the lowest hardware resource, so that it can be adaptable in any setting. There has been some work in this field to bring deep learning model closer to clinic. For example, AI imaging incubator, they provide a complete workflow from data storage, AI tools in a container, and also a visualization tool for medical image. However, as you can see in their backend here, they have their all the image of the patient in the centralized database. Even though it might comply with the policies, but it's still prone to leaking patient information to some certain threat. And another limit for this project is that it's only limited to DICOM, GIFT, and NIFTY format. So that's why it may not be easily widely used for the clinics yet. There are also some commercial and open source projects like NVIDIA or XNet, but they may exclude many users with low budget from accessing the technology. And XNet, even though it protects the patient data and have a good visualization, but they don't support AI models. And that's why we want to propose a comprehensive tool to bridge the gap between deep learning model and clinician. And the tool would not only not require storage of patient data or any software installation, but also support an easy to use visualization for many different formats, and the capability to run on any hardware, CPU or GPU. So this is a workflow of our proof of concept. First, you can train the models in any framework of your choice, say TensorFlow, PyTorch, sklearn, and then convert it into Onyx format, which is then be integrated by Onyx runtime, which is a package that allow you to do inferencing in JavaScript. And the deployment can either browser or Electron app, and that will be optimized based on your device hardware, CPU or GPU. I know that many of us might be skeptical about browser if it's safe for patient data, as we stated in the challenge. But in this application, we want to leverage the idea of progressive web application. And the basic idea of this is to use the browser technology to run it offline. So there will be no central server. That's why patient data will be secure and protected in the sandbox within the browser. But it's still user-friendly for clinician because it requires no setup and clinician is already used to using a browser. Maybe not many of you have heard about Onyx format. And because in this field, there are many different frameworks for machine learning training. But however, they have different characteristics, and some of them may be good for fast training and some would support a complicated neural network. And that's why it depends on the developer to choose which framework that is best for their use. But let's say you train the model in sklearn, but you cannot run inference with it. That's why you want to go into PyTorch or other framework to run inference. And that's where Onyx come into the picture. It helps because different framework would have different graph representation. So you have to go through an intermediary to convert between them. And Onyx help to do that job. And it's very flexible. That's why we choose Onyx as our universal format. It supports most of the popular frameworks. So you can choose anything you want and convert into it. And its interpreter, Onyx runtime, has proved to reduce the latency by almost 15 times. So we want to test it in our application. In this proof of concept, we have the visualization, and in the backend, we have a model to do mass segmentation for the brain. And we first trained it in TensorFlow and then converted it to Onyx. And here is a quick demo. So you can click the play button to run the inference. And it takes about 30 seconds with single thread to run the inference. The image will be then loaded directly into the canvas, which, okay, here. And then you can build it directly in the canvas like this and then choose, do some other function with it. So that's only the simple model that we implemented. But in the future, we want to support multiple inputs and more complex model. Another thing about Onyx runtime is that it modifies the model. So there might be some change in the accuracy, and we want to test that as well. Finally, we want to work on model distillation and compression for faster inference. So that's my work, and any feedback or comments is welcome. Thank you for listening.
I hadn't heard of this Onyx format before myself either, so it sounds really interesting. And I'm trying to wonder if it's even possible. It sounds so. It describes a kind of, it's a specification for machine learning models, but every machine learning model. And I'm wondering what happens with hyperparameter values. Do they also are they included as part of the Onyx specification?
So you're wondering if this format is included for every framework?
Yeah, I'm wondering if every machine learning model
Because
part of it, or if it's sort of being developed?
right now, if you use CPU, if it's run on WebAssembly, because for GPU is not, they're still working on it, but for
Yep.
CPU, they have support for for all the operators. So you can run for any models, but it still need to be tested before you actually deploy inside the browser, inside with JavaScript.
Okay. Right.
Rather than having a PyTorch to TensorFlow translation and so on.
Yep.
X model, and it basically, if you convert to that, then there's a single converter from that meta format into the other formats that are required by MXNet and PyTorch and so on. So it's just, otherwise you have to build a converter for every pairwise system. So if you only, so now you do two steps, you go to ONNX, and then you have an import from that. And we've tried the ONNX, and it works pretty well for the ArcFace model, converting it from one to the other. But if you try to do direct translation, it's very buggy. So nobody's putting much effort into direct translation anymore. Everyone's doing, the ONNX is becoming the de facto.
Okay.
That's the best path for moving from, say, PyTorch to TensorFlow.
Yep. So I can sort of see how it works in the wonderful world of building blocks of deep nets and stuff like that. But if I come up with a new cool activation function tomorrow that I claim is better than every other activation function, that's not going to be in there, right? So is someone going to incorporate that in there? Is that my job, or this is probably not a fair question, Stefan?
Yes, so we had some issues with that. For example, TensorFlow has a 3D transpose convolution function, and that wasn't included in Onyx. And then basically, yes, you go to the GitHub repository, make a pull request, and then you need to implement it if you have something weird. Exactly. If you have a weird activation function, you need to do it. So it's basically a mapping. Exactly. So it needs to know what do I describe, and then as a mapping from TensorFlow to Onyx, and then from Onyx to the other functions. And yes, if that mapping doesn't exist, it will just fail and say, I don't know what a 3D transpose convolution is, for example, and then it will just stop. Yes. So that's the limitation of.
Actually, Onyx actually supports you to build the custom operator yourself. So if you have some very strange operator, you still can add it into the into Onyx model after converted it, before converting it.
Interesting. Okay. Thanks very much.
Good morning, everyone. My name is Kenneth Uwopen, and okay. Excuse me. How do you? What? Yeah, I see. Oh, it's okay. Okay. Yeah, sorry about that. My name is Kenneth Uwopen, and I'm a PhD candidate at the University of Queensland School of Law, and my supervisor is Professor Greg Forrest. But that information is at the bottom. My research is on autonomous shipping law. Just like every other field or every other sphere of human endeavor, shipping is not immune to the disruption of automation and digitalization. And we already have researches and pilot projects going on as to the feasibility of autonomous vessels, and then what challenges exist and how those challenges can be met. And so my research is, part of this ongoing contribution towards solving that problem. So what I'm going to talk about today is the legal issues that arise from autonomous vessels. And it is specifically about charter parties. When it comes to carriage of goods by sea, carriage of goods by sea is so important to international trade and international and national economics, to the extent that about 90% of goods, transported across the world is done by ocean transports. And so it is necessary and important that we deal with these issues. So when it comes to carriage of goods by sea, there are two documents by which you can, two principal documents by which you can effect carriage of goods by sea. One is by charter party, which is a hire of a ship. So a charter party is a contract whereby the charterer charters the carrying capacity, the entire carrying capacity of a ship, or the principal part of it, for purposes of carriage of goods by sea. And so the contract, which contains the terms of the contract or the terms of the agreement, is called charter party. Now, in contradistinction to charter party, you have carriage of goods by sea, which is usually evidenced by bill of lading. Like if I want to transport, let's say, crude oil from Brisbane Port to Hamburg in Germany, I can decide to charter a ship, the whole ship, and then carry the goods, carry the crude oil by that ship. I'm the charterer, there is a ship owner. Then, if what I have do not fill the whole carrying capacity of the ship, I can decide to just get maybe another charterer who has chartered from another ship owner to carry the goods from Brisbane to Hamburg by way of bill of lading. So, but I'm dealing specifically with charter parties. And in charter parties, there are three types. In charter parties, there are three types. We have the voyage charter party, in which the contract is just for you to carry the goods from one named port to another named port. Then you have the time charter party, which involves carrying the goods over a specified period of time. Then you have what we call the bay boat charter or the demise charter. In short, even from the word bay boat, it's bay, the boat is bay. So, and the difference or the differences between these three types of charter parties is determined by whether it is the ship owner that has control of the management of the vessel, the operation and management of the vessel, or whether it is the charterer. In time charter party, in voyage charter party, and in time charter party, the ship owner retains control and management of the vessel. But in bareboat charter party, and when we say control and management, we are talking of who now employs the crew members, the master or the captain, and then the crew members. So in time and the voyage charter parties, it is still the owner who employs them. And then whatever mistakes they make fall on his head. Then in Bebo Charter Party, the charterer is now the one who employs the crew members and the captain. He maintains the ship, insures the ship, and whatever mistakes those crew members make, like hitting another vessel, those mistakes will fall on his head. So the question is, since what determines which category of charter party exists at a particular point is who controls the vessel and then the crew members. What is the implication, or what are the implications of the fact that we are now talking of vessels that will not have crew members? We are talking of vessels that will be replaced, that the crew members will be replaced with software and algorithms. And if there are mistakes in the algorithms, like if they start executing proxy goals, as one of the speakers said yesterday, and then such execution of proxy goals result in harm, who bear responsibility for them? And so there are 3 levels of autonomy. Sorry, there are 4 levels of autonomy. The first level of autonomy is, it doesn't give rise to too many complexities. Because in the first level of autonomy, the vessel is with automated processes and decision support, but you still have crew members on board. So it is just like the traditional vessel or ship. Then in level 2, the vessel is remotely controlled. But so which means there are 2 parts now. You have onshore, maybe based on land, and then or offshore, because the control center could also be based on the sea, like you have oil rigs. But you have the vessel itself. So instead of talking of one entity now, we're now talking of 2. But at least for this second part, you still have crew members on board who are operating this ship, probably with assistance from those at the control center. Then level 3 and level 4 are what we are concerned with here. And in level 3, there is a remote control center, which could be located on the land or on the sea. And then there is the vessel. But the vessel now does not have any human being on board. So it raises a lot of questions. Then you have level 4, which is fully autonomous vessels, which is just like driverless cars. So vessel is on the sea and nobody is on it. There's what we call allocation of risk and responsibility in law, which is if software, as I have said earlier, if software starts executing proxy goals, which result in harm, who will be responsible? So if you put vessels on the sea, because traditionally, under the principle of what we call vicarious liability, which is the crew member, if they make mistakes, then the ship owner will bear it. Now, who will bear the mistake? Is it the software programmer? Is it the manufacturer of the ship? Or is it the ship owner? Especially when injury or harm is caused to a third party. Remember, we are within the realm of contract law. And in contract law, there's what we call privity of contract. So which means if I enter into a contract with you, it is only you and I who can benefit from the contract and who can also suffer burden. A third party cannot. So who bears responsibility? In shipping under charter parties, there are obligations that each party bears. So most of the times, parties expressly provide for who should perform which obligation. But in the absence of such express provision, there is implication in the law. Such obligations will be implied against one party and in favor of the other party. So the first one we'll want to look at is obligation to provide a seaworthy vessel. This is just like on road transport. For you to put your car on the road, it must be roadworthy. So for you to put your vessel on the sea, it must be seaworthy. And because the existing legal regimes or the existing legal rules were conceived of with a ship with human beings in mind, a vessel cannot be seaworthy without having human beings on board. And so what that means is that if you put an unmanned vessel on the high sea, it may not be considered seaworthy. And a lot of implications can arise from this. It can even be detained at the port of discharge. So if you send a ship that doesn't have human being on board from Brisbane to maybe Antwerp, and is not yet recognized in Belgium, the Belgian authorities will seize it, and so it's not seaworthy. So what that means is that there is need for amendments of some of the existing rules to accommodate the new arrivals, so to speak, the autonomous vessels. Then there is the obligation to provide a seaworthy vessel is on the ship owner. Then there is obligation to provide or to nominate a safe port or safe bet. So if parties usually provide expressly, it can be you have obligation to nominate a safe port. If that becomes the obligation, then the charterer, once the ship enters the port, then the ship owner has performed his obligation. Even if there is no bet is where it occurs. So it's just like, let's say that you hire a car now, and the obligation of the car owner is to bring the car in Brisbane. There is no, provision that it must be parked somewhere. So if it comes to Brisbane City and you can't find any car park, he has performed the contract. So if he's staying for the next 30 days looking for a car park, you are paying him for, extra for the duration of his stay here. So that is the difference between bet and port. So, but if the obligation is to nominate a safe bet, even if the ship owner has stayed there for 30 days and he has not found a bet, then he has not performed his obligation. So why this is important with respect to autonomous vessels is that although the charterer has obligation to nominate a safe port, the port is considered safe when a ship can reach that port, use that port, and leave that port without being exposed to danger, absent unavoidable occurrence. So a port only needs to be prospectively safe, which means if I'm sending a vessel from Brisbane to maybe Rotterdam. And at the point I'm nominating the port in Rotterdam, I know that there is non-connection. Electricity is not working there. What it means is that as we are talking, it's not safe, but there is expectation that before the ship gets there, they would have rectified the problem. So it's prospectively safe. So assuming a ship is sent to a port, and before the ship gets to that port becomes unsafe. The master or the ship owner need not proceed to that port. He can ask for fresh orders. And then the charterer has obligation to issue fresh orders. That is to nominate another port. And where it becomes complex is if it is a software vessel, which is moving, let's take fully autonomous vessel without no human involvement, moving to a port. For that vessel to be able to know that a port which was prospectively safe but has become unsafe is now unsafe, it has to be able to, have a kind of situational awareness, data gathering. So that is where machine learning, robotics, and all this come in. And if it is not able to do this, it means that the ship owner has failed on his own part of the bargain. And assuming this happens, who will bear responsibility? So these are some of the things we are considering in this research. Then you have the loading and discharging operations. By law, the loading and discharge operations should be, on the ship owner, but usually parties expressly provide that it should be on the charterer. And currently, the loading and the discharging operations are done manually, but it is expected, especially as has been experienced with respect to MV Yara Beckland, is a Norwegian ship, and currently is moving between two ports and is expected to be fully autonomous by 2024. So if the loading and the discharging operations become automated as well, it might now affect these obligations, because currently, when there is loading and discharging operation, there is intervention by the charterer from outside. But if it becomes automated, then he may not come in. And then even if there is mistake, or if there are mistakes, then we still have to now analyze who should be held responsible for those mistakes. Then you have maintenance and repairs. It's one of the obligations. Obligations for maintenance and repairs is on the ship owner. He must maintain the ship by keeping all the, certificates, surveying the ship, and making sure that the ship is up to date in terms of certificatory requirements. And then if there is breakdown, he needs to replace or to make sure that things are, repaired within a reasonable time. And this within a reasonable time is within a reasonable time of his actually knowing that there has been a breakdown, or within a reasonable time of when he ought to have known. This is what we call constructive knowledge. He ought to have known that there was a breakdown. So if the vessel is humanly manned vessel, it is possible to attribute a captain or crew's knowledge of the breakdown. Let's say in the middle of the ocean, it is possible to attribute that since they knew, he ought to have known. But now we have, let's say, fully autonomous vessels, and then the ship just broke down in the middle of the sea. how will the ship owner know? So this will affect the people's, the parties' rights and responsibility. Also, in the traditional ships, you have engineers who are on board, medical doctor, you have, if there is someone is sick, someone will attend to them. So now you don't have such engineers on board. So this will also affect the performance of this obligation. Okay, so where you have most of the problem in this control center, where you have a control center either on the land or on the sea, how do you deal with this, especially with respect to arrest of ships? Arrest of ship is one of the ways by which someone who has been injured in the contract of the carriage, in the shipment, can obtain remedy. So if a ship is in Brisbane now, in Brisbane port, you can get a judge to order the arrest and the ship will be arrested. It can't move again, either the ship or the sister ship. But for a court to have jurisdiction over a ship, that ship must be physically present in that city or within the jurisdiction of that court. But now we are talking of a situation whereby the control center may be on the land, but the ship is somewhere in Asia or maybe in Europe. So do we now say that the presence of the control center here in Brisbane now gives the court jurisdiction over a ship in, outside Australia? So these are also some of the issues, that will arise. And then we'll have the one we call salvage. If you voluntarily help in saving a maritime property in distress, you can claim salvage. There is no need for there to be a previous contract. So the question, but it must be a marine or maritime property. So the question is, if there is, like, let's say fire now in control center on the land and someone helps in saving it, will this qualify for salvage claims? And yeah, thank you very much. And I'll be happy to take your questions.
And we have another speaker to come down. Yep. Any questions for Kenneth? So I'm wondering, I'm thinking about the kind of transition from mechanical to electrical to software and now to automated software. So if something goes wrong with a ship and it's mechanical, my intuition is it's often easy to prove and to explain what happened because the fault is clear, like the engine caught on fire or something. But with AI, with algorithms, it seems to me it's much more difficult maybe to prove what was the cause of the accident. I don't know if that makes sense. Do you have any comment?
If it is mechanical, as I've said, there is obligation for maintenance and repairs. So assuming it is known that it's mechanical, in cases of traditional ships, there will be engineers who could work on it. Yes. So, but if it is autonomous and it is mechanical, the first issue to just be disposed of is that since it's mechanical, it doesn't concern the software programmer. So whether he's liable or not will not come in. But if we don't know how it came about, as in the mistake now, how it came about, some people are, proposing what we call strict liability, and then product defect liability. So once you have shown that there was a problem, then the ship owner should be held strictly liable for the injury that resulted.
Thanks very much, Ken. My name is Paul Hinman from the School of Social Science. Thank you for that very fascinating presentation. It demonstrates the way in which technology is not a simple replication of humans doing something, a replacement of humans, and everything else stays the same. When we automate, we fundamentally change some of the legal principles in some cases. And in the case of robo-debt, which we have hearings here in Brisbane today, is another illustration of the way in which an automated system fundamentally changed legal principles. What's suggested in your discussion, in your conversation there is that if the ship is autonomous, it also speaks to the designer of the ship and not just the owner or the charterer. And I wonder, to what extent does the designers of the ship feature in legal responsibilities at the moment? And if they don't exactly feature in the legal responsibilities now, do you see that would be something that needs to occur legally, more so because of autonomous shipping?
How much, if they owe and to what extent they owe such a responsibility depends on who is making the claim. So if someone goes to ship builders or ship construction company and say, I need a ship, and then they design the ship and the ship is defective, he can maintain an action against them in contract. But if he has, been using the ship to carry goods, remember, it's possible for someone in Lagos to use the same ship to carry. He doesn't even know who the builder is, who the manufacturer is. Yeah, so between the manufacturer and the ship owner, he will claim in contract. But between the third party, maybe the ultimate consumer, he can claim in what we call neighborhood principles, which is that if you are manufacturing goods, you should expect that you owe a duty of care to whoever is going to use that good, even if it's 100 miles away. And if there is a breach in that duty, he can make claim in negligence, but it's difficult to prove. You have to prove that he owes a duty of negligence, that he breached the duty, and then that duty is resulted in care, in harm, and it's usually difficult to prove. Yeah. So, but if it is software, so we are thinking of product liability regime, and then we are thinking of negligence, and then strict liability. So, if at the very worst, the person who has suffered injury can claim against the ship owner, and then usually ships are insured, so he can get from his insurance, or he can make a kind of a secondary claim against the shipbuilders.
Okay. We had a question or Lorenzia online had their hand up, but I don't know if we can hear you, but you could try and ask this question if it's quick.
Yeah. Can you hear me?
Yes, we can. Yep.
Thanks. Hi, Kenneth. Great presentation, and thanks for explaining that. I'm wondering, will you analyze all 4 levels of autonomous ships, or will you focus on just one level of autonomy? Because you mentioned there are 4 levels, and yeah, 4.
So you are talking of labor law, right?
Level of the autonomy.
Oh, okay. Yeah. So my research is on the rights between the charterer and the ship owner.
Mm-hmm.
Yeah. So when you are talking of labor law now, you are talking of the right between the crew members and the ship owner or the charterer. And I guess that when you are talking of labor law, you are talking of the structural unemployment that will result if we automate ships. Or if you automate ships, the current crews will lose their jobs. And of course, they will be able to maintain claims in labor relations against whoever was their employer. Yeah, but a lot of research, could be done from various perspectives: part planning, machine language, because even the current rules are written in human language and they cannot be understood by machines. So we need statisticians, mathematicians, and programmers to be able to convert the language into machine readable language. So what I'm doing is it doesn't cover labor law. Yeah, but there are issues of labor law also that will arise.
All right, thanks.
All right.
Good. All right. Let's thank the speaker again.
Okay, so I'm going to give you a talk about my poster, and the topic is the preparation for AI with the help of novice human workers. Okay. So with the help of the novice human workers. So I believe that you have seen so many amazing AI models and powerful AI projects. And now I have a question that what is the first thing to be done before you build your own AI models or AI projects? So from my perspective, I would say that the data preparation is the most important thing to be done. Because based on my experience that if low data quality always leads to the low performance. And now we are living in a big data era, and every user just are producing the data every day, and those data are very informative. We can use some machine learning techniques or some data mining techniques to find some useful information. However, I would say that those kind of data sometimes could be corrupted. We can see so many kinds of data quality issues. For example, the records can be duplicated and records can be non-unique. And it's common to find some format inconsistency issues, right? And you can find some missing values, or you can find some imprecise values. So those kind of virus of data quality issues are very common, and you have to deal with that. And to achieve a higher performance, to achieve a better model, right? Unfortunately, a study shows that data worker can spend 80% of their overall time to do the data preparation. So this kind of data preparation activities has no beautiful figures, no takeaway messages, no outputs. You just do the data preparation. So it's time consuming and it's tedious, right? So we have to consider how to do it wisely, right? And you have actually 3 options to do that. The first one sounds good. You just use the machine to do that. We have some data profiling tools. So in my talks, there are some terminologies, but you don't have to care too much about it. So today I'm going to talk like the data curation, data cleaning, data profiling, or data pre-processing. So those kind of terminologies, you don't have to find the difference. So we are just towards the data preparation here, right? So we have so many data profiling tools. And for example, DBMS, they can help you to generate some like metadata automatically, and you can get some simple statistical results. For example, the mean values, median, and find the maximum value, minimum value. So those kind of statistical results. It's very easy, right? And you don't have to use the human to do those kind of issues. But the problem is those kind of machine-based solutions are lack of the in-depth understanding of the data, right? And another challenge is that those kind of algorithms, machines are designed for some specific type of data set and some specific kinds of task. So we are lacking, we lack of a general solution or unified workflow for the data cleaning process, right? So that's the drawback of the machine-based solutions. And we can have the second option that we use the human workers to do that, especially we can say the data experts, right? So they can write some codes, write some scripts flexibly based on the requirements in some like Python, Java, or some other programming languages. So it's possible. And the good thing is they can adjust their solutions based on the requirements. They are flexible, right? But the drawback would be they should put considerable efforts. Like I said, at most 80% of their overall time to do that. So it's very time consuming and tedious. So actually the state of the art works are investigating the third option, which is called the human in the loop option. So they are building some hybrid algorithms, hybrid systems to combine the human and machine. So they can take the advantage from the human, which is the flexibility, and they can take the advantage from the machine, which is the scalability. And in the human, in the loop system or algorithms, we can find that human and machines, they are in their correct positions, and we can combine them wisely and get some amazing outputs. So that's what I'm going to say today, the human in the loop system. So is that all? I don't think so. Because like I said, most of the activities are done by the data experts, right? So they are in shortage and they are expensive. Convey involves some novice human workers in the data cleaning or data curation process. So that's what I'm interested in, right? So based on this point of view, so we propose a lab study called the DataOps for G. So for G means for generalists. So we are doing a comparison against the specialists, data specialists, right? So we build a platform for the generalists and call the DataOps for G. A question is how to support them effectively, because the data generalists, they are lack of data expertise, right? So to support them, we involve a terminology called the data ops. So what is a data ops? We just bundle some codes like the Python scripts into a button. They can just click on the buttons, input some parameters. They don't have to write any code, and they can use, like we have the regular expression builder or generator, you can say. They don't have to write regular expressions. They can just use the tools we provided to generate some amazing outputs, right? And the scope of our work, we are investigating the generalists to discover the data quality issues like the duplicates, non-unique or missing values, imprecise and inconsistent. So we would say, see that can those kind of generalists use the data ops and use the built-in functions to find those data quality issues and do the annotations for our data sets? And can they generate some comparable results compared to the specialists? And to do the evaluation, actually, we are doing the evaluation from two perspectives. The first one would be the effectiveness. We are talking about the accuracy of the outcomes and the efficiency. So efficiency means their time spent and their behaviors and their strategies. So we do it from two perspectives, and we use the F measurement to do the evaluation. So we use the F1 score to represent the quality of their tagging, right? And on the right, you can see, I just put some results here. It's not all the results we got. So this paper has been accepted by the TKDE. So if you're interested in this work, you can to search .ops4g in TKDE and you will got the full paper. But now I would like to say the results shows that our platform can actually support the generalists effectively and efficiently. And another figure shows that actually we find there are some points there to show their performance. And the figure shows that different workers has their different advantage. For example, a worker could be good at find imprecise values, and another worker could good at find format inconsistent issues. And can we design a combination like we just let these workers to do the imprecise values and the other workers to do the inconsistent values? So we are giving the opportunities for those kind of combinations. And beyond this work, actually want to put it even further. So we are talking about the novice human workers here. Do you know there is actually a state-of-the-art method called the cross-sourcing? This is the advanced technique that you can use some cross-sourcing platforms like the Amazon Mechanical Turks. You can use the system to post your tasks and assign to different workers. It's very efficient. You can recruit a large group of people to do your task, to do some human annotations. It's good for your AI models and it's good for your AI projects. So please use the cross-sourcing. And we also build a work called the data scanner for C. So 4C means for crowd workers. So actually we are doing a human machine hybrid way to solve that problems. Because in the 4G, we just produce some data ops to support the workers. And now in data scanner for C, we are doing it in the human in the loop system. So the workers choose the records flexibly and the machine to scale up the data, like the human can choose 5 records and the machine propagates the outputs to thousands of records. So that's our thinking. And this has been accepted in the HComp 2022 and will be presented recently. Okay, so if you are interested in this work, you can go to the HComp 2022 to see our demo. And to summarize the takeaway messages here, the first message is the human in the loop system can actually help you to build your own AI models, and you can use some humans to do the hard part for the machines, and you can collect some human annotations from the cross-sourcing. So please consider the human factors in your AI models, and maybe they can help you to deal with some challenging problems. And the second message is, if you are collecting some bad results or results with low performance, please don't question your workers first. Maybe you should consider that. Is this your problem? You have to have a better task design. You have to build some tools. You have to build some, provide some functions for them, and you have to ask them wisely, right? So our results shows that actually generalists can produce some comparable results comparing against the specialist. So please design your task wisely and provide them powerful tools, and they can give you some better results, right? So that's two takeaway messages. And that's all for my presentation. Thanks. And any questions?
We have run a bit over time, and sorry about that. I might suggest that we just leave questions for show into the coffee break if people have questions. And now we have to slice the coffee. So we have about 15 minutes for coffee, and then we'll try and start again at 11:10. Just about to get started.
Yep.
All right. Good to go then.
Oh. Is that mic positioning all good? You can hear me? Sweet.
Excellent. All right, so time to start the next session, and Matt will be our first speaker. It looks like I'm chairing the session again. Whenever you're ready, Matt.
Okay. Hey, everyone. I'm Matt, and today I'm talking about what I've been working on, decoding cosmic structure with neural networks. I've been working with Yuan Sen, Tamara, and Rosanna as part of Astro here at EQ. And I'm in my first year of PhD, so cruising through for now. As a bonus, throughout this presentation, all of the space imagery has been generated with DALL-E 2. So I think it does a really good job. If you're not looking too hard, you wouldn't be able to tell. So cosmic structure. When I say cosmic structure, your thoughts might go to something like this. So this is an image from the James Webb Space Telescope. This was this year. And it's a really pretty image. It's got stars in the foreground. It's got some galaxies in the background. And the galaxies are what I'm most interested in. So there's a bit of sort of interesting lensing going on as well. That's cool physics, but not what I'm into today. I'm more interested in the actual positions of the galaxies. And particularly when you zoom out a little bit. So on the right here, I have an image of, well, this is data from a sky survey where we've looked up at a spot in the sky and taken the positions of all the galaxies and then taken a slice through it. And you can see there's all this interesting sort of structure. There's clustering, there's these like long filament parts, and there's just a lot of information in the way that that's all formed. And just as a bit of scale, every single dot on that is an entire galaxy. So we're talking something like the whole Milky Way is a single dot in that image. So the actual scale of everything here is pretty immense. As a cosmologist, the number one thing we're interested in is working out a good model of the universe. And that's a very general, broad thing to do. But ideally, we want it to be able to explain what's in the universe, explain the laws of physics, and explain the starting conditions. So how it started, maybe Big Bang, something like that. And the model, if it's good, should be able to predict everything we see today, from stars to galaxies to all the exotic stuff like black holes. And importantly for me, it should also be able to predict the cosmic structure. So all of these shapes that we see in the large scales. Our current model of the universe is actually pretty good. We've come to a pretty good understanding of it. So what that lets us do is run simulations. So what we're looking at here is a simulation basically over the span of the entire universe's life. And there's a lot of really cool stuff happening here. At the moment, things are collapsing under gravity. And then you'll start to see things sort of pushing outwards. And this is galaxies forming and radiation pressure, and there's electromagnetism moving things around as well. It's a really complex, chaotic system. And I guess if you look at this, you can kind of see if we tweak the parameters a little bit, if we change the model, if we add a bit more dark matter, or we change the settings of gravity, then the whole structure will completely change because of this sort of chaotic system. It also means we get to look at really pretty simulations. So after that's finished running, we get out some structure maps. So what we're looking at here is a slice through one of these simulations. After it's been run, we're looking at a density field from what's left over. And it's a good sign that we see, again, the clusters, the filaments, because this roughly matches what we have actually observed in reality. But we can actually go a step further. If we take a simulation for a whole bunch of different models of the universe, if we play with the parameters, we can get a set of simulations, and then we can compare that to our own universe to work out what seems closest. So this is from the Abacus Summit simulations. And this is what happens when we change the model of the universe a little bit. Hopefully that one's a bit smoother, yes. So what we're doing is running the simulation all the way through, but with slightly different parameters. And you can see the changes it has on the sort of structure and the end result. And so by looking at this end result, we can sort of backtrack and figure out what initial model we started with. So the idea of simulation-based inference is to take those sims, take the real data, compare them, and pick which one is the closest. So then whichever one's the closest, we kind of expect is going to be a good idea of what the model of the universe is actually like. But unfortunately, picking the closest sim is not exactly a trivial task, because we're never really going to know what the initial parameters of our own universe look like. Like how did the seeds start? Actually figuring out what's closest is a little bit difficult. To illustrate this point, I am going to give a cat-based example of simulation-based inference. So let's say we have a cat simulator, and we feed it in 50 centimeters, 150 centimeters, and 200 centimeters as the lengths of cats, and it spits us out these three. Then let's say we have a data cat. If I ask anyone in the audience, how long do you think this data cat is if we've got these three simulated cats? I think everyone would be able to tell me what they think pretty quickly. Seems pretty obvious. But if we're using the wrong metric, then this becomes a more difficult task. So let's say, okay, I don't know anything about cats. The closest cat is clearly going to be the one in the middle, because our data cat is all black. The cat in the middle is all black. They're obviously similar. So therefore, our data cat has to be 150 centimeters long. Now, obviously, that's not right. So what we've done there is we've used a bad extraction of information. If we want to use a better one thing we could try is comparing the length or the width of the eye to the width of the nose. In our data cat, that's about 1-to-1. And if we look at our simulated cats, that'll give us a pretty good idea that our cat is probably around 50 centimeters long, right? So this is the difference between extracting good information and extracting not so good information from our fields or our simulated environments. So the main point, extracting information more efficiently lets us infer properties of the cat or our cosmology field better. So what would be a good way to do this? One starting point would be to take the mean density of the fields. So if I take the mean density of the simulations and the data field, compare those together and pick the closest one, so maybe the one with the least difference, then, okay, we should have a better model of the universe. So let's actually do that. here's some data from the Abacus Summit simulations again. On the y-axis, I have the mean density from these simulations. And on the x-axis, I have the model of the universe's matter parameter, omega m for anyone that's into cosmology. And so now, with this information, if I observe a section of the sky and I see we have a mean density of around about 0.8, then we know our model matter parameter should be somewhere around 0.6 to 0.8. Right, that mean density has given us useful information. But when we do this with a different parameter, say the model clustering parameter, sigma 8, if the mean density in the sky is 0.8, then maybe the model clustering parameter is about 0.2, maybe it's about 0.6. We don't really know. It doesn't contain that information. So one better way to pull that information out is to use something called the power spectrum. I'm not going to go into too much depth about what the power spectrum actually is because that requires a bit of background. It's a little bit mathy, but essentially it just is a good way at pulling information out of the field, and it's very commonly used. But we can do better. And surprise, surprise, it's using AI. So in this case, I'm talking about convolutional neural networks. So CNNs are really good at pulling out shapes, sizes, intensities. And when you've got lots of layers, you get out a lot of interesting higher order information as well. So sort of clusters of clusters, you can start reaching that information as you add layers. So this is potentially a good way at pulling that information out of the fields. So the idea is we'll train a simulation, train a CNN to predict each simulation's model of the universe. So whatever model, whatever parameters, whatever model of the universe the simulation was run on, we want to be able to predict that using just the output fields. And then we could simply feed the real data into this same CNN, and it should spit out a model of our own universe. In practice, there is a few more steps here, and generally we want to have some sort of uncertainty bounds. We want to know how good our estimation is, so we can play around with other ways of doing this, introduce Bayesian likelihoods. We've been also looking into using normalizing flows. So there is a few more steps, but the general and the main idea is that using these CNNs, we can extract that information better. As an extension also, we've been looking at, well, the filters for general convolutional networks. The first layer tends to look something like this for all sorts of different benchmark CNNs. So this one's from AlexNet, but you tend to see these sort of stripy patterns with different scales and different orientations. So if you want to skip the whole learning process for the convolution filters, we can actually do that with one way is to use a scattering transform. So this is a method I've been using a fair bit lately. There is a couple more parts in the background, but essentially it works as a convolution network with fixed convolution filters. And there's a few advantages to doing it this way. So a general CNN is highly flexible, but it can be prone to overtraining and it's difficult to interpret a lot of the time. And that interpretability, it's been talked about a fair bit throughout this workshop. And I think that especially applies when you're working in something like physics. Our actual goal is to understand the universe better. We don't just want to go from A to B. We want to know how we went from A to B. So having these n-body simulations are currently limited because n-body simulations are incredibly expensive to run. They take up to months and months, especially if you want to do a whole suite of them with different models of the universe. It takes a very long time. Having that little extra robustness means that we're not going to overtrain, and just because the filters aren't are fixed means that we're not going to overtrain on that data. They're not as flexible when we fix the filters, but it still manages to extract complex information. So just as a quick example of some actual results, on the bottom here, I have the true value for a set of simulations for the matter parameter, the clustering parameter, and another parameter called fluid parameter. And on the y-axis, I have the prediction from when we've run the scattering transform on them. And you can see basically the one-to-one line means we can predict it based on the simulation outputs. So that's a good sign and promising results. Still early days for all of this, but happy to see some promising stuff. So just 3 points to leave you with. Cosmic structure is highly complex, but really rich in information. Comparing simulations to observed data is going to let us study the properties of the universe. And when we're doing this, CNN-style architectures let us access more information. And when we go ahead and fix the filters, it can help improve robustness and our interpretability. So that's all from me for today. Thanks very much.
Thank you. Question time.
Thank you. That was awesome, Matt. So Shirley Ho's group have shown some really impressive generalizability of using CNNs on cosmology simulations, showing that you can, put in exotic theories of gravity and then get out the parameters of those exotic theories of gravity quite well, even if it was never trained on that. I wonder, which direction are you taking this sort of approach?
Yeah, I've come across some of that work, and it's really interesting stuff. And it's definitely sort of one of the directions to take. The main spot where I'm sitting at the moment, as I said, first year PhD, I'm sort of still figuring out my way. But I'm generally going to be comparing these simulations to DESI data, Dark Energy Spectroscopic Instrument. It's a new survey, state of the art, and it's got a lot of structure. We're going to get a heap of structure information out of it. So I will be comparing this data to the simulations because that's still fairly new. A lot of the work that's previously been done is just showing we can compare simulations to other simulations, which is exactly what I showed in the last slide, mind you. But the actual comparing to data is yet to be worked on a fair bit. And there's going to be, no doubt, a lot of issues along the way. When you do a real survey, you've got so many things blocking you. You've got holes in the sky from where everything's in the way, and the actual shape of it is different. And there's going to be a lot of things to take into account there. So that's going to be one of the focuses. Oh, yep. Yes. So Sheikh says, it appears your scattering filter-based CNNs are just Gabor CNNs. And that is absolutely true. Gabor filters is one of the ways you can add that. I don't think I would have seen that paper, so I'll have to check that one out. But in particular, our filters are Morlet wavelet filters, and the actual scattering transform process adds a few extra steps. Since I have this prepared, so I'll use it. So the other changes that we do in the scattering transform is we change the convolution layers to fixed convolutions. ReLU nonlinearities are really common in CNNs, but we change that to an absolute value because our convolution filters are complex. And then instead of max pooling, we just use a spatial mean. And these have some math properties that people a lot better than me at math have worked out, are very useful, and they're very stable to deformations. So that is one advantage over just doing this in a pure CNN way, as one of the advantages of using the scattering transform. But yes, absolutely, I'll check that paper out. Thanks for that link. you very much.
And then I need to share the screen.
Yes.
Yeah.
Should be fine.
Thanks. Hi, everyone. This is Xingwen, and I'm a postdoc from School of ITEE, working with Dr. Shix on MRI reconstruction. So today I will be sharing our recent work on undersample MRI reconstruction with site information guided normalization. Yeah, so you probably know about MRI, which is really good because of its soft tissue visualization and it is non-invasive in nature. But if you have experienced MRI before, you probably know that MRI is really slow. It takes a long time to acquire a single MRI image. So the main problem to be solved in MRI is to accelerate the imaging process. So talking about the imaging process, you may need to ask, why is that really slow? This is because when we generate MRI images, we need to acquire the signals sequentially like this in the measurement domain. And then by taking the direct inverse Fourier transform, we can get an MRI image. So one direct approach to accelerate the process is to acquire less data, then it will be accelerated. But the problem is that after the acceleration or the subsampling, the images, if we just directly taking inverse Fourier transform, the image gonna be really blurry like this one, and we cannot use it to do the diagnosis. And there have been many works on solving this problem, which means if we have some undersample measurement, can we use deep neural networks to reconstruct the high quality images? So one popular work is the D5C5 to do the MRI reconstruction. So what is that? So basically doing the MRI reconstruction is an inverse problem mathematically, which means for example, in this equation, we have xt2, that is the image that we want to reconstruct. And then we have y, which is the measurement, and a is the operation like Fourier transform. So by taking xt2 equals to a inverse y, we can directly get the image. But the problem is that during the subsampling process, a is not invertible anymore, which means there might be many xt2 that satisfy this equation. And we cannot find a single xt2. So we have to build an optimization problem where we have two terms. The first term is to ensure that this equation is satisfied. And based on that, we will have some regularization term that can be decided based on the property of the images to regularize the optimal solution. And then we need to find the xt2, the image. And conventionally, there are many image properties, like the image can be sparsity in some certain domains. But with the help of deep learning, we can use some convolutional neural network to represent the regularization part. And then normally by taking some optimization method like gradient descent, we can get the optimal solution by doing iterative optimization. So in our baseline work, they take the convolutional neural network like CNN to do this kind of reconstruction, which means the input of the network can be a blurry image, and then it can go through some of the convolutional blocks. It can be really simple, like just going through 5 convolutional layers with some ReLU activation functions, and then go through a data consistency layer, which corresponding to the data consistency one that we mentioned before, to make sure that the reconstructed image is consistent with the sampled measurements. And then we can do that iteratively, which means we can do a cascade of these ones and then get the high resolution images. So this is a kind of baseline approach to reconstruct high quality images. And then in our work, we find out that MR images actually present various appearance based on factors such as views, anatomies, and acquisition protocols. For example, in the image I show here, both are the A and B, both are brain images, but you can see from a different view, like a sagittal view and axial view, they present in different style, in different like appearance. And so that's the pair B and C here. Although they are all axial images, but they can present different contrasts. Like the B is more bright, while the C here is like T2 weighted image is in a different contrast. And from the previous work, it has found that this appearance-related set information can affect the deep learning-based undersample MRI reconstruction frameworks. So the main aim of our study is to know the effective use of such set information, such as views or contrast in deep learning-based undersample MRI reconstruction. So what we did is that we proposed a set information guided normalization module where we encode this set information into the network. So for categorical information such as contrast or view, we can embed it as the embedding vectors. And then for the continual information, for example, like the acquisition parameters like repetition time or echo time, we can stack them as vectors. And then after going through some of the nonlinear mapping layers, we can output the normalization parameter like gamma and beta here, and then we can use that to normalize the feature map. The good thing about our proposed module is that it's ready to insert it into any of the baseline architecture. For example, this is the D5C5 that I showed you just now. And then we can insert our proposed sign module after the convolutional layers in this baseline architecture. And then we conduct the experiments to see the effectiveness of our proposed method. So we conduct experiments on the publicly available data sets, which include a brain data set from the NYU Fast MRI Challenge, and also including other database. And we also conduct experiments on the knee data sets. And the set information here we investigate include the contrast, like the one I showed you before, T1 weighted, T2 weighted, and also the view, like the slices from this data set are sagittal view, but this data set has an axial view slices. And also the source, which means like the scanners, which scanner is the images from, and also some scanning parameters like TR and TE. So that's the knee data sets. And then we conduct experiments on the acceleration rates on 4 times and 6 times case. And then we use the SSM and PSNR as our evaluation matrix. Both of these matrices are the higher, the better. So this is the quantitative comparison. The undersampled results is shown in the first row here. And then by using the baseline architecture, D5C5, we can get an improved PSNR or SSM. And if we insert the sign module, you can see the results is further improved. So this is the case of 4 times acceleration. We also conduct experiments on the 6 times acceleration. We can observe the same trend. And here is a visualization of the reconstructed image of a sagittal brain image. So this is the ground truth one, and this is the undersample image. You can see it's quite blurry and full of artifacts. And then by using D5C5, we can reconstruct a good image. And this is the region of interest of the image. And then by inserting the sign module, we can get further improvements. You can see the detail is further preserved compared to the original baseline. And the box here beside the region of interest is the arrow map. You can see that the proposed method has a smaller arrow. And then we further conduct the studies on other backbone architectures. So we also use an OUCR backbone, which is also very promising in reconstructing MRI images. So again, we insert our sign modules after the convolutional layers. And then here is the results. We still get better results compared to the original baseline. So that's the 6 times case. And this is another example of the proposed method on the OUCR baseline. You can see this is the results of the OUCR reconstructed image. It looks promising, but with the proposed method, it further improved the detailed information. Yeah, so that's all. In conclusion, we propose a sign module that can encode the set information as normalization parameters to improve the undersample MRI reconstruction. And we have conducted more experiments and analysis, and you can refer to our paper for more information. So that's all. Thank you.
Super efficient, Karen. Well done. Yes, questions.
Oh, thank you.
Awesome talk, really liked that. I think a lot of those techniques will have applications in radio astronomy, and we should probably talk about those at some point, because radio astronomy is the 2D analog of 3D MRI. And so one of the things I was wondering is, given MRI is three-dimensional, I don't really understand why it matters whether you've got an axial or a sagittal view, because you could just rotate it in the voxel space. Maybe I don't really understand.
Yeah, so that's a really good question. So basically here in the experiments, we only test on 2D cases because we assume the acquisition is in 2D plan, which means we reconstruct each 2D images and then stack them together as a 3D instead of doing a 3D acquisition. So the sequence is not in a 3D way, but in a 2D way. So, so that's the first part. And then also, think about the volumes. Some of the volumes, the doctors may need to examine the XL for some of the disease, but for others might need a high resolution in the sagittal view. So it doesn't mean every volume is the same resolution in each of the dimension. So that's why sometimes we have sagittal in high resolution, but if you say it from the XL side, it's low rise because we can just skip some of the slices. We don't need the volume. The same for the other way around. We can get a really high resolution XL, but we don't need to have all the slices along all, like, you know, the volume. So it won't be like all high resolution, I think. Yeah, so that's why we have XL and sagittal and treated it differently. Yeah, but I guess it's extendable to a 3D case, but just don't consider the view anymore, but only like other attributes. Yeah, that's that. Oh, okay. Oh, yeah. The question here is that is sign different from ADA-in? So yeah, ADA-in is the thing that we used in last year's AI seminar at UQ, like the same place as well. So ADA-in is the adaptive instance normalization. I think ours is quite different because we use kind of a hypernet to estimate the parameters. So which means we categorize some of the information together to output some of the parameters. But in ADA-in, they don't have this hypernet. It's more like you change the gamma beta, then change the style of the feature map. So basically, in the ADA-in case, the gamma and the beta is learnable, but in our case, it depends on the input. Yeah, so the work is inspired by ADA-in, but I think that's an extension of adaptive instance normalization.
Okay. Other questions? Yep. Excuse me.
Just wondering, the mean and the standard deviation that you use, is that like for the entire data set, or is that just for the batch level?
So the gamma and the beta, the mean and standard deviation here is only for the specific feature map. So like instance normalization, like each slice has a different mean and variance. Yeah, but in such way, it can group some of the information, because if you know these slices are in the same contrast, which means they don't have the same like mean and standard deviation.
Okay. Anyone else? Right, if not, let's thank Karen again for her talk.
Thank you.
think this is me. My name.
Let's check the Zoom. Definitely. Check. To that, we should be fine. Yeah, okay. Yep. Good.
All good. Okay, cool. Thank you. Thank you very much for having me. There's been some great talks this morning. I wasn't able to make it to all the talks yesterday, but I'm sure many of them were very good and the ones I saw were very good. So, oops, let's make this full screen again. Yeah. Okay, cool. So my name's Benjamin Pope. I'm in the School of Mathematics and Physics, and I'm an astronomer, as is Matt over here. So I'm very excited to be in what's quite an active computational imaging session today. And that's sort of the context in which you should see this. But I'm also going to be telling you about things that are not strictly machine learning, not strictly AI. I'm actually interested in completely deterministic processes that we can model completely deterministically. And so, as you'll see, this turns out to be actually very similar. So I'll be presenting work that I'm doing with my PhD student, Louis Desdois. I used to be at the University of Sydney. He is at the University of Sydney. I believe he's joining us on Zoom though. And we're talking about automatic differentiation as applied to optical modeling and what we can use it for in astronomy. And I hope in other fields as well. I'd love you to approach me about that. So if people want to follow along on these slides online or take anything home or see any links, here's a QR code and a link. These slides were all written. This is actually my little other experiment in AI this week. I used Corto, the new document rendering package, which renders between LaTeX and DocX and HTML and stuff to render these slides. And I did so in VS Code with GitHub Copilot. And so I would love you to pick out what of the slide formatting was suggested automatically. That was a bit of fun yesterday, learning how to use that. So this is the context of what we're doing. Here is an image that is my desktop background and probably most other astronomers' desktop backgrounds. This is one of the first images produced by the James Webb Space Telescope, which is the largest space telescope in the world, or rather off the world now. It's 6.5 meters wide with an unprecedented quality of detectors and sensitivity of wavelength coverage all the way out to the mid-infrared from sort of red light. And it's doing amazing astronomy. At a cost of $10 billion, you'd hope it would. Every hour of this telescope has an amortized cost of about 100 grand. So I'm very excited to have a couple of dozen hours across the various programs I'm involved in of planned James Webb observations, most of which haven't been conducted yet. So I'm only looking at sort of public images here. But I'm interested in doing high angular resolution astronomy, so directly imaging planets. So here is a picture of the Carina Nebula. It's very pretty. There's a whole lot of swirly gas and dust there from which stars are forming, is the context. Lots of people really care about that dust. I don't. I care about these stars. You can see them and you can know that they're stars because they have that 6-pointed star arrangement, right? And that's called the point spread function. Who's heard of a point spread function before? Computational imaging people. Okay, cool. PSF it does what it says on the label. You take a point source like a delta function of light, like a very distant star, which you can't resolve. And it's the spread function, which says how the light spreads out on your detector according to a particular function, right? And so this PSF is something I've been thinking about for a very long time, the James Webb PSF. When I started my PhD, it was supposed to be launched by the end of that PhD. That did not happen. I've got grey beard now. The PSF is the 2D Fourier transform of the arrangement of mirrors in the pupil, we call it. It's the pupil in the same way as your eye has a pupil. It's the entrance aperture that light enters the telescope on. So the 2D Fourier transform of the pupil gives you this point spread function, which blurs out every point source in the image. In fact, you convolve the true scene with your point spread function is how you get the imaging, right? Now, this has got a particular hexagonal arrangement of mirrors. Here's a photograph of it being tested on the ground, not in space. And so this particular hexagonal arrangement Fourier transforms to this sort of six-pointed star with a little couple of little cross beams for the struts that hold the secondary mirror, right? Now, here's the trouble. It's the Fourier transform, but it is the complex Fourier transform. So you care about the phase of the light across the pupil. And by phase, what we mean is the advanced or delayed position of the wavefront of this light through your telescope. So here's a little simulation. On the left, I've got a zoom in of the core of that point spread function I simulated for an ideal James Webb with completely perfect mirrors. And on the right, I've got a simulation where you can make the PSF look like a pizza if the mirrors are a little bit misaligned. Now, that's really exaggerated for effect. I've put quite implausibly large misalignments on those mirrors. But here's the issue. If you're looking for planets, and that's what I do, if you're looking for planets, the Earth is 10 billion times fainter than the Sun. Jupiter is only, about 10 times brighter than that. So you're talking about a contrast of 10 to the 9 between a star and its planets. Now, if you've got a very young star with young planets that are still hot from the process of their formation, you've got a contrast of 10 to the 4. Oh, easy. And you want to look at resolutions that are comparable to the size of this PSF, what we call the diffraction limit, because it's controlled by diffraction physics, right? So here's the trouble. If you don't know the mirror alignments, you're toast, because there are many, many possible arrangements of mirror misalignments that'll give you all sorts of funky speckle patterns. So what you have to be able to do is you have to be able to model these and somehow deconvolve a high resolution, high contrast image, given low resolution, low contrast data with unknown point spread function, which is controlled by all these misaligned mirrors. And okay, I know this sounds a little bit niche. It's the James Webb Space Telescope, right? But this is the ultra high tolerance case of something that's completely ubiquitous in imaging science and in optical science in general. This is nothing to do with telescopes. This is fundamental optical physics. This is the same physics as determines the speckle pattern of a laser when you shine it on a wall. This is the same physics that determines the resolution of a microscope looking through a turbid medium. So a lot of computational imaging people really, really care about getting high resolution images of cells or whatever. It's the same physics, right? And I want to work with people on that. So I'm interested in basically 4 problems. Two problems with 2 use cases I really want to say here. And they are in fact just conjugate, right? So I'm interested in data analysis, image analysis. Okay, I've taken a picture of some stars. Cool story, bro. Are there planets in that picture? Okay, now I have to deconvolve those stars and look for high resolution little speckles next to them, right? So I need to be able to model PSF really, really well. So this is a data analysis problem. I have no control of the hardware. I just get the data and I have to infer all of these unknown parameters using some kind of Bayesian inference or some machine learning or, whatever you like, right? This is the same as optical design. Because in optical design, I've got a simulation of an instrument and I'm going to put my mirrors here and blah, blah, blah. I'm going to do all that sort of stuff, right? And I'm trying to engineer some objective function to be as good as possible. Now, this is just the same thing. In data analysis, the objective function is I'm trying to engineer in my simulation something that matches your data. And in hardware design, I'm trying to engineer an objective function that has desirable parameters, right? And what's really cool is that all of optics is a subset of neural networks mathematically. In fact, optics is completely isomorphic to a subset of neural networks. And here's why. So optical systems are made of layers. Each layer is a global linear transformation where light propagates between some kind of optical elements like lenses or mirrors or something. And then at those points, you get an element-wise that is local, potentially non-linear operation where you affect the amplitude or the phase of the light, right? And so here's an example where you've got a coronagraph, which is a common kind of optical component for high resolution imaging, high contrast in astronomy, right? Where you put the light in, it goes into your first pupil, we call it, and then you focus it down. And then this is a device for blocking out starlight to look for planets. So you block out starlight in that plane, but you can't take an image in that plane because you've literally put a little metal piece in that plane to try and block out light. So you let the light that wasn't blocked come back out of focus again, and then you do something else to it. There's still a bit of light left over that didn't get blocked by that thing. And so you undersize the first pupil, so you block it out there, then you bring it back to a focus and put a camera there, right? And so this is an example of a very common architecture. This is actually called the Leo coronagraph. There's dozens and dozens of different architectures for coronagraphs. This is the first one that was proposed. It's not actually a particularly modern design, but it's a nice illustration. Now, the other thing I wanted to point out is this slide, all the text was written by GitHub Copilot when I put in prompts. Isn't that amazing? What? Okay, I was saying yesterday, could it put me out of a job? And I just tried to like, okay, so I put in some prompts about what this talk is about. Can it fill in one slide? Yes, it can. That's really scary to me. All right, and so to put this in language that people in other fields of machine learning might use, this is what we might call physics-informed neural networks or simulation intelligence, right? Where some people would use the term a physical layer. That is where there is a simulation of deterministic physics that occurs, but you do it all in some autodiff language so that it's completely integrable with neural networks, and then you're all, good to go. Right, and so just here is a picture of like a review paper on simulation intelligence, which is a big buzzword. Physics-informed neural networks are a big buzzword. I've got a DP under review at the moment. You can believe I put a lot of buzzwords into it. Okay, cool. So here's the bit I'm sort of trying to sell you. With Louis Desdois and Jordan Dennis, who's an undergrad at UQ, principally Louis, we've built Deluxe, a framework for differentiable optical modeling in JAX. Who uses JAX? Oh man, really? No one? Who uses PyTorch? Oh man, I'm going to cry. I've bet the wrong horse. No, JAX is really fast. It's way better than PyTorch for high performance applications. It has a worse ecosystem for machine learning, but a much better ecosystem for physics. I'm hoping to convince people to use JAX. Equinox is a neural network framework for JAX. So we've written it all in Equinox. So you can define an optical system by a series of layers, just as you would like a Keras model or something. Equinox got quite a similar API. So you go like, we're going to make an object that carries metadata about the light coming in. We're going to tell it the position of the light. Then we just put a circular aperture, we normalize it, and then we do a Fourier transform, a matrix Fourier transform to get to the output image, right? So I just want to click through to the documentation. Ah, no. What the hell was that? Oh, okay, sorry. New features on these Quarto models, right? So we got this package, it's on GitHub, it's open source, it's on PyPy. We're about to do a 1.0 release when the papers are out. And I just wanted to show you some examples where basically you can define metadata, define your optical system as a series of layers, and then bang, you can get a PSF by simply just calling the optical system.propagate. So here's a PSF, right? Now, what you might want to do is infer the phases, just the aberrations on the pupil. I actually got my eyes tested on Sunday. It's exactly the same thing as you do on an optometrist. They give you a list of numbers. That list of numbers is called the Zernike coefficients, that are coefficients of a particular polynomial expansion of the aberrations. So I've got the Zernikes for my eye now on a piece of paper, and I bought some new glasses from Oscar Wiley. This is what we're doing for this telescope. So we've got simulation, got some aberrations on there. And we do exactly what you would do in machine learning. We use Optax, which is a JAX optimization framework, to do ADAM, which everyone probably knows. We do ADAM and we get, bang, loss function goes down, great retrieval of the model. Now, there's actually something I really wanted to talk to people about. My favorite thing in here is that we can actually optimize a design towards the Fisher information of something that we want. Who knows what I mean by Fisher information? Right? Okay, so the Kramer-Rao bound says, and every statistician in this room is, I'm going to choke because I'm going to omit a couple of layers of expectation value in this statement. But broadly speaking, the Kramer-Rao bound says that the inverse Hessian of your likelihood evaluated at your expected values gives you a lower bound on the precision with which you can retrieve some parameters using any algorithm at all. This is fundamental mathematics. This is not like, oh, well, I've thought of a cleverer algorithm that beats the Kramer-Rao bound. No, it doesn't exist, right? So if I want to design a telescope that will optimally infer something about, the position of stars relative to one another is the example we have here, given some noise processes that we can model, we can do that because with AutoDiff, You can write down your likelihood, which is going to be like a Poisson likelihood of photons landing on your detector. And then you're going to do a Hessian of that with respect to all the system parameters, right? So here is our weird telescope. It's called Ptolemy, and it's hopefully going to be Australia's first space telescope. Here's a crappy PSF that you start with. Now we're going to define a likelihood, get the Hessian of that, invert that. That's our objective function. We're going to pick the determinant or the entropy or various, matrix norms we could put on that. Loss function goes down with Adam, coefficients go well. And so you basically go from a really ratty looking PSF to here is a telescope design with a really, really nice PSF that measures these stars really well. And not merely does it measure them really well, it measures them better according to the entropy. I think we've done it in different versions. I think this is the entropy of the Fisher information, right? So cool. How do I make this go away? Anyway, so we can use Hamiltonian Monte Carlo to fit models to data instead of Adam. There's all sorts of stuff we can do. I'd love to talk to people about it. So what's coming next? So we're about to submit version 1.0. I accidentally put the wrong text on that slide. This is what I wanted. So the important thing is, I think we have applications outside of astronomy. This is a really nice computational imaging tool for astronomy. We're quite proud of it, but astronomy isn't where the money is. Microscopy, lasers, cameras, this sort of stuff is all the same fundamental diffraction physics, and I'd love to talk to people about it. Anyway, thank you. Shows I shouldn't use Copilot for making these. It was fun though.
Okay. Wow. There were a lot of things to think about there. Questions?
Oh, thank you.
And we should also check the Zoom chat in case somebody pops a question up there.
Jack's user here says Shakes Chandra. Awesome. And Louis confirms it was the entropy, not the determinant of the Fisher information. Who does computational imaging? We've already had some talks on it. I know that there's at least two people in the room who do.
I mean, I think this is not really a question, just a kind of observation that I'm sure you're right that the stuff you're doing has applications in other things that people are doing around UQ. And part of the reason we run a workshop like this is because UQ is such a big place. And as AIs become more popular, one of the things I always observe is that you can have people who work in the buildings next to each other basically reinventing the wheel because they don't know that the person in the building next to them is also doing something that's essentially the same thing. So I'm happy to have a chat to you afterwards. And I mean, there are some people in our school who do optical stuff. I'm thinking Alex Rakic and people like that. I don't know about Joel Carpenter.
Talk to Joel.
Talk to Joel already. Yeah. But yeah, then beyond that into microscopy or the MRI stuff, I wouldn't know, but I expect there are people around who are interested in that. Yep. Okay.
Great talk. Thanks, Ben. I was just wondering, that funky telescope that you showed at the end, is that, have I understood correctly that is an optimal telescope formation to minimize your point spread function?
Yes. So where is it? Yeah, Fisher information. So here's what we're doing. I glossed over that a little bit quickly. So the stars Alpha Centauri AB, the brightest stars in the pointers, are the closest stars to us. They're quite bright. They're actually in a binary system. That's why there's Alpha Cen A, Alpha Cen B. They're not separated by a lot, about 20 arc seconds. That's the kind of resolution we're working at. And there's good reason to believe that there are planets around.
And so we want to look at the orbit of these at extraordinarily high precision, micro arc second or micropixel precision, in order to look for small relative motions that would encode the disturbances to the orbit caused by planets, right? And so Peter Tuthill, who was my old mentor and Louis' co-supervisor, is PI of the Tolleman mission, an Australian mission, to observe Alpha Centauri b at very high resolution and look for these motions over the course of a couple of years. And Tolleman's going to have a cool little mask in it of liquid crystal, which causes the light to diffract into a really weird PSF. And so what we're trying to do, and this has to be binarized, and we had to think of clever algorithms for binarizing it, right? This PSF has to be optimal for measuring these micropixel image registration is the problem people might be, thinking of. These micropixel shifts in the presence of all sorts of optical distortions and noise and all that sort of stuff. And so, yeah, we optimize this design in order to get a PSF that has the most information possible about position, relative position of those two stars. And so, yeah, we build a Fisher information matrix that includes all sorts of parameters, including separation of these stars, but also Wernicke aberrations that are the prescription for the optical aberrations. You don't want your telescope to be short-sighted. You measure its astigmatism, its coma, its spherical aberration, same things as with an eye. And we put all of this in, and we want to get the most possible information out of this PSF. So yeah, we do atom gradient descent on this objective function, which is the entropy of the Fisher information matrix. We see that these coefficients of a basis that we choose to represent this tend to converge towards fairly stable values and get you this really, really sharp, cool, high symmetry PSF there. And yeah, I mean, here's contours of the different parameters that we want to measure. And we see that the optimized ones are green and the previous ones are blue, and the green ones are always tighter, strictly tighter, because we have optimized those contours specifically. So yeah, it's fairly optimal. Of course, this is it's a multimodal posterior, I think, in terms of there might be many solutions to this. And so when we're actually engineering it, we're going to have to put a little bit more work into it than this example. But yeah.
Great, thanks.
Thanks.
Not knowing much about astronomy.
Yeah.
Australia is very famous for its work with radio astronomy.
Mm.
It's all optics.
Yeah.
Just wondering why the focus on optical for the planetary research, or is radio still useful, or is it, why choose one over the other?
Well, radio astronomy is very important for many areas of astronomy. It's half the astronomers in Australia are radio people, sort of half are optical. The thing is, though, almost everything you see in radio astronomy is a black hole. The great majority of radio sources in the sky are stellar mass black holes, or sometimes neutron stars or something in our own galaxy accreting matter, or the supermassive black holes at the cores of other galaxies also accreting matter, because you need very, very energetic processes to cause radio emission. And so very few ordinary main sequence stars, and certainly no planets, have been found until very recently using radio astronomy. Now, actually, that's what I work on. Other than this is the search for planets using radio astronomy. And so with collaborator Joe Callingham in the Netherlands, we've been using the world's most sensitive radio telescope, LOFAR, to look for highly polarized sources. So that's a whole other Bayesian problem of cross-matching optical and radio sources to try and identify planets as opposed to black holes. And we certainly claim to have found about 5 planets using radio astronomy for the first time. So hopefully this will be a really big thing when the Square Kilometre Array is commissioned in Western Australia over the next decade.
Basically, but both techniques complement each other and help in the search.
Oh no, very much so. So optical astronomy, certainly it's easier to see planets, but what radio astronomy tells you about is the magnetic environment of the planets and any magnetic connection to the star and its stellar wind. And so it's a very faint signal. Only LOFAR, this most sensitive radio telescope in the world, has been able to detect anything so far. But the Square Kilometre Array, which is actually an upgrade of sort of the same technology of LOFAR, LOFAR is a pathfinder for the SKA, is we project going to discover hundreds and hundreds of these. And we hope to be very firmly involved at the forefront of that.
I've been hearing about it for a long time. Is there an ETA for?
Geez, that's a very tough question. It's like James Webb. James Webb when I started my PhD in 2013, it was going to be launched in the next 2 to 3 years, and it was launched at Christmas last year. The square kilometre array had a similar timeline for commissioning 2017 or 2018, and I think we're expecting 2027 or 2028 for full operations. And it's not going to be a square kilometre. They had to de-scope it. And so de-scope indeed being a pun. So the actual SKA that's being built is about 0.1 square kilometres. And it's phase 1 of a probably vaporware plan to actually build the nominal square kilometre as phase 2. You know, major projects are tough. Oh, yeah.
Okay, we better move on, but
Thank you.
Thanks again. Right, and last presentation.
Yes.
Can you hear me? Oh, that's better. Good morning, everyone. My name is Jian Wang, and I'm also the last presenter today. And I will try my best to not push you from lunch too far away. Okay, I will try to finish my talk in time. And as you may notice, in the first version of our schedule, so my original presentation title was injecting out-of-domain knowledge by frequency factorization. So that's my latest research. But then I think about, okay, this is a AI collaboration workshop. Then how about introduce some real life industry project together with AI? Wouldn't that be more interesting to the general audience? Then it comes to this topic, when AI meets agriculture. So agriculture is a data intensive discipline. So the image of crops, sensor data, or say the weather information can be gathered every single day. So this also brings a huge opportunity for the data scientists to participate, to be engaged in a series of the tasks. For example, data acquisition, data management, analytics, prediction. Those tasks can facilitate the digital agriculture. So in this presentation, we will demonstrate you how artificial intelligence can be used in the agricultural domain, and also the current challenge we are experiencing. So as you know, advanced machine learning algorithms are developed for computer vision, NLP, and recommender systems. Okay, so those techniques can be used for the image data, text data, or time series data. And in agriculture, this kind of data types are like everywhere in various scenarios. Okay, so here I will just give you a bit of idea of AI in agriculture to list several applications here. So for example, crop yield prediction, price forecasts, intelligent spreading, in predictive insights, for example, when is the best time to sow the seeds to get the maximum productivity? Okay, we can also have the agricultural robots, crop and soil monitoring, disease diagnosis. So how machine learning works? Come on, it's the second day of the workshop. I believe most of you must have a good idea of the answer of this question. Let me just give you a quick review by showing the this penguin classification example here. So first of all, we need to gather a label training data. So in this case, our label training data could be bill length, depth, body mass, and most importantly, the corresponding penguin species of this record. Okay, so after we gather this set of the data, now we can get a designed machine learning algorithm to leveraging the underlying knowledge of this data set to formalize or to construct a machine learning model. And then next time when there is a new penguin record coming in, the machine learning model could tell you, okay, which species is this penguin data. However, it's applying machine learning techniques in real life agriculture application as simple and ideal as this penguin example. Actually, let me just paraphrasing this question a bit. From how to apply machine learning techniques in agriculture into how to identify the limitations of existing machine learning algorithms, handle potential issues in real life scenarios, and design effective strategies to apply machine learning techniques in agriculture. Let's have a look of this weight hat detection problem. Okay, so this problem is to help crop yield prediction from a crop images. Okay, so to achieve this objective, so first of all, we need to have our annotators to take a photo from ground and then trying to label out where is the weight hat. And then after we get this labeled data, we can use our object detection model to train the model. And then if there is a new picture, new ground level weight picture coming in, then the model can detect the where is the weight hat in the image. And we can see from example here, our current object detection model can perform this job pretty good. So that we can conclude, okay, supervised object detection is easy for the ground level images. However, ask a human being to carry a camera on the ground. It's quite ancient way, right? How about we pursuing a more modern and more effective way? Now we are want to hiring a UAV, which is unmanned aerial vehicle, to take the image from the sky. Okay. It comes out some challenges. For example, you see, we listed some image here. So, which is ground image, image from 10-meter high sky, 20-meter high sky, and 40-meter high sky. We see that, so those images are different from the original image in both of the resolution or the image general style. Okay. Besides that domain gap issue, we also have the issue is it is a new task. So if we want to use a original supervised way, we need to ask human annotators to do the annotation from the very beginning. This will trigger very high human labor cost and time cost. So here we just demonstrate a example of directly applying our model trained on ground images to that 10-meter high UAV images and 40-meter high UAV images. Remember how good job we done on the original ground images. Now let's see about 10-meter high UAV images. Well, we still can detect some of the hats, but definitely it's not all of them. And the situation get even worse on those 40-meter high UAV images. So it is very bad generalization from ground images to these UAV images. So as we mentioned, so the domain gap between our original ground image and this UAV image mainly from two aspects. So one is image resolution, and the other one is the image general style. So it naturally comes to us this solution. So can we use the developed image super resolution model to increase the bad resolution and make our model more adaptive to the new situation? So to train this image super resolution model, we have two things as the input. So one is the ground truth. So the other one is the downsampling image. So the objective is asking this downsampled image to have the same resolution with the original one. So that when there is coming a new testing image, it can increase the resolution of this image. However, it is not that ideal as we thought. So it cannot help with object detection as the produced image is still not in a good quality in terms of the texture information. Then apart from the resolution difference, we also have a large difference is the image style. So the image style of the ground and the UAV image is largely different, as you can see from the others, from your left-hand side. So we are trying to adopt the style transfer module to transfer the UAV style into our ground style. So here on the first row is a simple example to show you how style transfer works. So in style transfer, we have basically like two input things. So one is your original content image, and the other is the style image. So what you want to do is trying to transfer the style of the style image to the original content, so that we can produce the third image here. So which is our image with our original content, but in the given style. So we're trying to, well, you can see in the first example here, it's doing a pretty good job. The original style keeps, and there's another fancy Van Gogh like style to add on the original image. However, when we apply this technique to the cropped images, to the UAV images, it's still not good enough. So the critical texture information is still lost. So there's some better and larger example that you can see. The texture information is not there anymore. So we can hardly use that to perform object detection. So how can we actually resolve this two limitation together at once? So two limitation is annotation cost and the domain gap. So why don't we just use the original UAV image as the training scene? Because, well, we don't have label, but we have machine learning model. Can we use machine learning model to annotate it? Answer is yes. So here we introduce some progressive pseudo labeling strategy. So first step, well, we have a trained ground level image object detection model, right? So we use that model to detect 10-meter high UAV images. Well, we have this kind of results. So we can see the result is not good enough because it has some large overlapping bounding boxes and it cannot detect all the bit heads. But still, we can kind of taking that as a starting point. And then second step is based on a simple intuition. Because our UAV is on a 10-meter high position, right? So from 10-meter high position, if you look down to the weight heights, it should be roughly the same size. So we're just trying to remove those large bounding box that higher than double value of the median bounding box here. Okay, so now you can see that those inaccurate bounding boxes has been removed. So after this step, you can see most of the bounding box can locate a pretty accurate for the bit heads. And then we can use this pseudo-labeled image, trying to use that to train our object detection model once again, trying to fine-tune it. So we use this pseudo-labeled image, like not only one of them. So we have a set of it, trying to use them to fine-tune our machine learning model. And then here is our fine-tuned result. We can see this fine-tuned result has been already significantly improved compared with our original one. So that's our fine-tuned result for like the 40-meter high UAV images. So after the first round of fine-tuning, we can already see the significant improvement from the very beginning. So it comes to us, why cannot we just fine-tune it again? So we just do the pseudo labeling and fine-tune again. And now we can see that our model has been improved again, and most of the weight heads from 10-meter high can be successfully detected. And also we can observe some improvement on the 40-meter high UAV image as well. So we can see at the beginning, it's just very huge bounding boxes and it's not accurate enough. And then after the first round of fine-tuning, we can already locate some bit heads. And the second round of fine-tuning, we can get even better model. To conclude, from this real application, this real scenario, we can see that there is some limitations of machine learning. First of all, in the real world scenario, the training data is not always available. Even if it's available, it doesn't mean that you will have label of it. It can trigger a high human annotation cost. And also, machine learning models are not always off-the-shelf tools. It's not like, okay, it's online, it's open source, then I can just grab it and go. Plug in and play is not always the case. Okay, and then solutions is not always straightforward, so that it needs the practitioners to deal with machine learning model to improve the machine learning model case by case. So yes, so that's all for my presentation today. I'm happy to take any questions. Thank you.
Yeah, just looking at your approach, I know you did look at style transfer and so on, but my gut feeling is that style transfers to make things look pretty is not for actual measurements. You did use traditional signal processing in terms of bilinear upsampling for the high resolution, but you can do very, very good high resolution synthesis using neural network approaches.
Yeah.
Did you look at those as well?
Yeah, so actually the image super resolution we mentioned is a neural network approach. So we just one moment, let me just come back a bit. Yeah, so here what we are doing is using this one as a input to train our image super resolution model. And here is the ground truth, so that the objective of our image resolution super resolution model is to make this downsampled image as clear as our ground truth image. So that's the training objective of that image super resolution model.
There is there's a fundamental problem with downsampling. I did this with like face recognition. You get very wrong results by you try to simulate a blurry image by a mathematical transform, and it turns out that a true blurry image is quite different from what you get from a mathematical transform. So what you do is you learn the transform, not the real problem. You know, which is what you may have discovered here. So you know, going from a 10 meter or 1 meter to a 10 meter range when you have to use real data.
Yes, yes, agreed.
It's very
Yes.
hard to have real data that's actually aligned because you can't take exactly the same picture with two different.
Yes, exactly. Yes. Yeah.
Anyway, it's interesting. Well, we've done a lot of this with cell images because they have very wide range. It's on a microscope rather than a drone, but trying to go across those ranges and get good images. So it's yes, it's a similar problem, and we have like images that are like 56 gigabytes or something. Because a tiny little slide, when you put it on by 100 magnification, becomes the size of a football field. Yeah.
Exactly. Yeah.
Our team just try different proposals. Yes, but that's one of that. Yeah, which doesn't really work. That's why we usually don't try to and try to transfer the solution. None of them really works. Yeah, that's why we move on to the program data that will label it from any solution.
Did you have problems with like the sunlight being different and like the seasonal whatever variations on the ground?
So you mean the different weather factors like the sunlight?
Yeah, like on a cloudy day, the pictures would be different versus on a sunny day, for example.
Yeah, I think we have like a simple hypothesis is like most of the images are taken near like sunny weather, because if it's a different weather condition, then it will trigger a larger domain shift than what we have before. So it may make the scenario even harder. Yeah. Thanks for the question.
What will happen if the light sources, in the daytime and in the morning time and in the afternoon and in the noon period. So is the light affects the resolution, and we know that there are some pathogens, there are some fungus that attacks in the ground of the plant. So in that case, what will be your suggestion?
Thanks for the question. Let me just repeat the question a bit, see if I understand it correctly. So basically you mean, so different sun angles can trigger like different maybe shades so that it maybe affects the prediction results, right? Yes, so what you mentioned is also a kind of a domain shift. So for example, if you are only taking the image from the morning, so the shade could be just one angle. Yes, so from the image we have, so currently we don't see a big problem here for this case, although this is a certain kinds of domain gap. So neural network itself has a generalization ability. If it is not a huge domain gap, so sometimes the model itself has a good generalization ability to make a reliable prediction. Yeah.
So suggestion there from Shakes on the chat about
Ring transformer, yeah.
One of his favorite networks, maybe.
Yeah, yeah. So thanks for the suggestion, Shakes.
Okay, so let's thank the speaker again.
Thank you.
And that's it for this session. And that's all of the, I guess, accepted presentations for the workshop. So we have about an hour for lunch now. We want to start again here at 1:30 because we have exciting things this afternoon. We have a panel session at 1:30. And then there'll be a bit of a kind of closing sort of session with, we want to hand out a couple of little awards and stuff. There's this People's Choice Award that you can vote for your favorite presentation via this QR code. And we also have this survey thing that we want people to do to get your input about UQ and AI research at UQ. So that'll all be here this afternoon. So, and on Zoom as well, hopefully. So if everyone can come back for that, that'll be really awesome. Lunch and posters is up in Liveris again, same place as yesterday. So.
Want to remind people the People's Choice Award will be closing soon. So please do remember to scan, vote for yourself, for your friends, support each other. You can do multiple choices as well. And then we'll announce the result after lunch.
Thank you. I mean, participants could be here as well if you want. Okay, so we're going to get started now with our panel session for this afternoon. And I've kind of had this idea in my head for I don't know how long, but this year I finally managed to organize some sort of panel session to chat about the big picture of AI, and we've already had a huge variety of topics covered and lots of different expertise in the audience and also on the stage here with me. I have Professor Janet Wiles, Professor Paul Henman, Dr. Ian Wood, myself, representing different disciplines, different opinions, and I'll let everyone introduce themselves when you speak. So I had this at the beginning of the workshop. I showed a definition for AI that I wrote because I thought we needed something in 2022. And so I don't know if people remember that, but I'll quickly remind you. And then I asked the panel members to think about some